This lecture is on parametric equations and curves. So first of all, parametric equations involve a new independent variable we call the parameter, such as t for time perhaps, or theta for an angle. Basically, it's a new independent variable, so in this case we have x3 is 4 cosine 3t, y3 is 4 sine 2t quantity squared. So x and y are now both dependent upon another independent variable t, and for our window for something like this, we have our t value going from -5 to 5 in steps of 0.01. I've got an x min, x max of -6 or so and 6, and y min -4 and 4. Now if we take a look at the graph, what we see is it traces out in direction. In parametric equations, besides being curves, they have a directionality associated with increasing t or theta. So you have to be able to not just get the curve, but to show which direction it's going in. And so according to your t-step, you get better resolution if you use a smaller t-step, but it takes a lot longer to trace it out. Now maybe you see the direction switch now, so we're retracing back over our path, but our direction is the opposite way. So a smaller t-step, you get better resolution, but it takes longer. A bigger t-step goes a lot faster, but your resolution is worse. So as we see the t increase and come back around, now you see what sort of figure we're going to end up getting here, this sort of bow tie or pretzel shape. It comes back down to the x-axis. So let's just, to see what happens, we'll change our t value here, or excuse me, our t step. So instead of 0.01, if we make it 0.5, going from -5 to 5, goes a lot faster, but the thing is a total mess. So you have to find the correct trade-off in order to make this work. So other things you can do with parametric equations, which are a lot harder than rectangular, something like this. This is sine AT, x is sine AT, y is cosine BT. If we animate t around, we get this different shape, and you can imagine in terms of just x and y, this is a rather complicated function here, of course. And if we change our a values and our b values, we get different things. It takes a little while for the traces to erase. And then let's start this over. So changing a and b around is going to give us different shapes. If we get a and b to be about the same, let's see what happens there. If we get them to be both about 0.99, well, then we've just got ourselves a circle, it would appear. So that's a rather simple one we get out of that. Okay. Another parametric equation involves this idea of cycloids, given by x of theta is r times theta minus sine theta, y of theta is r times 1 minus cosine theta. And the curve generated here, imagine putting a light on a wheel and rolling the wheel, and it's what the light traces out. So if we see, as the wheel moves, we see the point around it. Right at the bottom, it's not moving. Midway up, it's going the same speed as the wheel. At the top, it's going twice as fast as the wheel, and so on. And so you get these little cusp points down here. And then what we can do is change this around, and now we take the wheel and we rotate it around another circle, and we trace out a point. This is called an epicycloid, and this shapes of this style, I believe, were posited by some astronomers who still wanted to hold on to a geocentric theory of the Earth, when it was becoming clearer and clearer that the Earth was revolving around the Sun in the heliocentric theory. We have, so this is called the epicycloid. Going back to the cycloid, here's the cycloid shape, and you see, imagine a car with square wheels, and if you wanted a smooth ride, you would want to be driving on a cycloid-shaped road, which has very little practical application, but it is somewhat interesting nonetheless. So that would give you the smooth ride in your square-wheeled car. And then we're not going to explore this very much, but you can also do parametric equations in 3D. Here's a real simple one, just a straight line in 3 dimensions. But of course, they can get significantly more complicated as we increase theta. This is giving us sort of a cylindrical spiral, and you can move things around to take a different look at them for what it's worth. This is sort of a conical spiral. This is now in something called cylindrical coordinates. We'll look at this one, cylindrical coordinates, sort of a mixture of polar and rectangular. Okay, moving on, it can be useful in graphing these things to eliminate a parameter. And so we'll look at different ways to eliminate parameters. Starting with this, if you have x of t is equal to t, y of t is equal to sine t, you can simply substitute and you get y of x equals sine x. Now that's good for some equations, but not for others. In this situation, x is equal to 4 sine 2 theta, y is 2 cosine 2 theta. If we solve this for theta, we get this expression. Plug it in here really is a mess. There's a much better way to do it. You square both sides here to get x squared 16 sine squared 2 theta. Square both sides here to get y squared is 4 cosine squared 2 theta. If we divide by 16 and divide by 4, we can make this into a sine squared and a cosine squared. When you add sine squared 2 theta to cosine squared 2 theta, you get 1. And so you see that you actually have the equations, using these parametric equations, are the equations of an ellipse. Here's another thing to watch out for. If you have x equals rad t, y is equal to 2t squared, we can take both sides to the fourth power to get x to the fourth equals t squared, and then plugging in x to the fourth for t squared, we have y is equal to 2x to the fourth, which would be the curve in green, but you have to make sure you keep track of domain and range effects of doing this. Of course, x can never be negative because square root of t will never be negative, so keep in mind that you're really only looking at the right side of this, and the arrow would be going to the right because, again, there's directionality associated with parametric equations. That's eliminating a parameter. Adding a parameter is really much more straightforward. We have y is 2 cosine 3x and x is t. Let's see. What we can do is just simply add in this. Well, we have this equation in red. To make it parametric equations, we can just make x equal t. Y is 2 cosine 3t, or if you feel like getting a little fancier, x is negative 1/3 t. Plug that in, so y is 2 cosine negative t. Since cosine is an even function, we have y equals 2 cosine t. Parametric equations can also be used to model projectile motion. We have two different projectiles. This imagine you have an object you're throwing out at this horizontal speed, 5t. It's dropping negative 4.9 t squared. That's the acceleration due to gravity from a height of 20. This one you're throwing out at a speed of 0.3 t. Less horizontal acceleration or horizontal velocity. Same vertical because we're throwing it from the same place and we're on the same planet. And if we graph these things simultaneously, what we see is that, well, that's not simultaneous. Let's go back and do it simultaneously. What we would see is that your horizontal velocity is not coupled to your vertical velocity. And so the effect of this is that one way to think about it is if you stand on top of a building and you shoot a bullet straight out and you drop a bullet at the same time, ignoring wind resistance and effects like that, they're actually going to land at the same time, just of course very far apart. So here's our two particles going down and they're dropping at the same speed and they hit at the same time. Okay, getting back into a couple book problems. This is just a quick example of graphing parametric equations. If you have x equals rad t and y equals 1 minus t, we can make a table of values, t 0, 1, 2, 3, and if t 0, 1, 2, 3, we solve for x and y, and we get the point 0, 1, the point 1, 0, 1.4, negative 1, 1.7, negative 2. These 4 points, you can kind of connect them up and you see the direction going with it. That's what the red arrow indicates. And if we eliminate the parameter, we see it's an upside down parabola. Of course, we're not going to include the left side because our x value has to be greater than or equal to 0 because of the fact that x is equal to rad t. This is an example of eliminating a parameter. So again, we don't solve for theta. We instead use Pythagorean identities. We square both sides here. Over here, we divide both sides by 2. And now if we add the two equations together, we'll have x squared plus y over 2 is equals cosine squared plus sine squared, which in turn is equal to 1. And then I can solve this for y and put it more in a parabolic form. But again, you have to realize that there are restricted domains and ranges. Cosine will never be less than negative 1 or bigger than 1. And this one, the y then will never be less than negative 2 or bigger than 2. So here I've just written in the domain. Okay, this is another example of eliminating a parameter, graphing a curve. So we'll use a Pythagorean identity, divide by 4 and square both sides, divide by 3 and square both sides. And the way to eliminate the parameter here is by subtraction. If we subtract the two equations, x squared over 16 minus y squared over 9, that's secant squared minus tan squared. The Pythagorean identity for that gives you 1. And so you see that these two parametric equations actually give you a hyperbola centered at 0, 0. Going horizontally, we go out 4 left and right, up and down 3 to get our box, gives us our asymptotes. So there's our hyperbola. And finally, a little bit more of eliminating a parameter. If x is e to the negative t and y is equal to e to the 3t, one way to do this is to solve this for t by getting t as negative ln x and then plugging it into the equation y equals 3t. So y is equal to 3 times e to the 3 times negative ln x. We put this up as an exponent, cancel the e to the ln, we get x to the negative 3. Another way to think about it is take this entire equation x equals e to the negative t to the negative 3rd power. And so then we have x to the negative 3, which is equal to e to the 3t, which in turn is equal to y. And then you've got to watch out again for your domain and your range.